So on page 28 now. Look at our ionic compounds. Some of them are soluble, and some of them are not soluble, which is insoluble. And when we're talking about solubility here, we're specifically talking about water. Okay? We're not really interested in whether it will dissolve in some other solvent. So we're talking about in water. And what we know happens is that if a substance is insoluble, an ionic compound is insoluble in water, then that means the ions in that compound are more attracted to each other than they are to the water, and so they're not pulled apart by the water. But for our soluble compounds, the ions are more attracted to the polar ends of the water molecule than they are to each other, and that's why they dissolve. So for us in a soluble state here, then we have the separate ions. That were present in the compound, along with water. And we always use AQ to indicate that they are aqueous ions. So aqueous meaning water. Okay, so these ions have dissolved in water. Our example in our booklet here, we've got some sodium chloride. And we have our solvent, which is water. And when we combine them together, this is called the solvent. The water is the solvent. That is the thing that it does the dissolving. Okay? And this would be my solute, which dissolves. That in my solvent. And that produces then a solution of sodium chloride. Okay, does that make sense? So we've just got a few words here. This one is a really important word, that you understand what a solution is. What's a solution? It's something dissolved in something else, basically. Okay, so we've taken our salt here and we've dissolved it in water, and so now we have a salt solution. These other words, solute and solvent, you don't have to talk. You'll use that when you're formulating answers, but it's probably helpful if you understand which one's which. Okay? The solvent is what we're dissolving in, just in case you strike this sort of language in the question. Now, if I have ions in solution, so I have two solutions, different compounds. And I combine them together. Sometimes the ions in those solutions react with each other. And they are going to then potentially, if they do react, they will form what we call a precipitate. And this is another word that you do have to know. Okay, so the ones that precipitate are the ones that are insoluble in water. That's why they've come out of solution in the form of a precipitate. Now, if we look at an example, just so that we can sort of follow through what's happening here. Just so I have a solution of sodium chloride, and I'm going to react it with a solution of silver nitrate. Okay, the AQ is telling me that they are in solution. That I could also be performing other reactions where they're solid, in which case I'd have an S in the brackets. But these are in solution. And this will form a precipitate. Now, how am I going to know which ones form a precipitate and which ones don't?
By swapping the partners and using your solubility table.
Yeah, looking at the solubility table. We already know that silver nitrate and sodium chloride are soluble, don't we? What we don't know is whether sodium nitrate and silver chloride are soluble. That's what we need to find. So that's what Jarek is meaning by swapping partners. This is soluble and this is soluble, so we want to know, is this soluble and is this soluble, where we swap them over. So if you have a look at your formula sheets and you determine, firstly, is sodium nitrate insoluble? You need your formula sheets out. And if we're looking on page 5, we have the solubility table for some common ionic compounds. It's divided into two sections. There's a section above a heavy line and a section below the heavy line. The section above the heavy line is saying that they are all soluble with some exceptions, and the exceptions are listed in the right-hand part of the table. But if we go below that heavy line, they are all insoluble with some exceptions, and the exceptions are listed on the right-hand side of the table. Okay, so if we think firstly about sodium nitrate, is this soluble or insoluble?
Soluble.
You think soluble?
Wait. Oh, wait, what?
So we're talking about the sodium nitrate. What are we going to look up on here to see if we can determine whether it's soluble or insoluble?
Nitrates.
Nitrates. And if I look across that row for nitrates, it says
All soluble.
all soluble. So that means that sodium nitrate is soluble as well as silver nitrate. All nitrates are soluble. What about silver chloride? Insoluble. How did we know that? Yes.
Because for chloride says all soluble except AgCl, BgCl.
Yeah, yeah. So we found it on there, and we can see that that is the one that is solid then, and that means that this one is the precipitate. Now, we can't form this without having had those other ions present, because we have to have our charges balanced. So in order to bring together the silver ions and the chloride ions, I needed to have the sodium ions and the nitrate ions present as well. But we call them, these are the spectator ions. Because just like at a football game or some other sporting game or anything else, you have the players who are participating. The spectators are there, but they're not doing anything. And that's how we can think of these ions here, that they're there and we need them, but they're not actually participating in the chemical reaction. Therefore, they're spectator ions. Okay. Now, when we're writing out our equations, it is important for us to balance our equations properly as well. We've done our naming, and we know that when we're naming, we have to have our ions present in the correct ratio so that there's no net charge. But we need to continue doing this when we are balancing our chemical equations. Okay, let's work through the example on the bottom of page 29, and then I'll stop talking. So we've got lead nitrate. It's lead 2 nitrate. So I know it has a 2+ charge on the ion, and the nitrate ion has a single negative charge. So I'm going to need 2 lots of NO3. I also know if I have my solution that all nitrates are soluble. And I'm mixing it with potassium sulfate. And again, I know that the sulfate ion has a 2 negative charge on it, and the potassium ion has a single positive charge on it. So I'm going to need 2 potassium ions for every sulfate ion to make sure that they balance out within the substance. Now I want to see, well, what will I produce when I mix, what are my possible products? It's going to be potassium nitrate and lead sulfate. Oops. That's not balanced at the moment. What do I need to do to balance it? Potassiums, I've got 2 nitrates. But potassium ion has a single positive charge and the nitrate ion has a single negative charge. So how do I balance? Yep, the coefficient number up front. And now if we look to see which ones are soluble, is there going to be a reaction here? Well, we already know that all nitrates are soluble, so we can say that this one is aqueous. What about the lead sulfate? Insoluble. So that means it's going to be listed as a solid. Now this is known as a full molecular equation. I'll do this a couple of times, but we'll introduce it now. Because what we have to be able to do is write net ionic equations. We start out with our balanced molecular equation. And anything that is aqueous, we separate out into ions. And this is for the full ionic. So I've got lead ions. I've got nitrate ions. But when I write it as a compound, I've got this little 2 here. What do you think I should do when I'm writing it out as a separate ion? Because this little 2 is telling me how to balance within a compound.
Do you put it in front?
Yeah, big number out the front is going to be so the coefficient. The same thing here for our potassium ion. What about the little 4 here with the sulfate? What happens to it? it going to move out the front as well, or is it going to stay where it is?
It will stay there because it's the full oxygen, not the healthy.
Okay, so it has to stay where it is because it's actually part of the ion. And let's keep going. Remember that we're only splitting up anything that has the AQ. So because the lead sulfate here is a solid, it's just written the same way. So that's a full ionic equation. I've written out every ion. But for a net ionic equation, we remove the spectators. And a spectator is anything not changed in the reaction. So anything that is listed the same on both sides of the arrow can get removed. Which things can we cross out?
The potassium and the nitrate.
Yep, we can cross them out. And that means our net ionic equation is just that. Okay, now we're just down to looking solely at what has actually reacted, the reactants and the products. Now, if I was asked to state which who would name the spectator ions, what would I call them? Which ones are the spectator ions? Okay, and what?
Nitrate.
So is that all right, what I've written there?
They forgot the charge as well.
Yeah, we need to have the charge on there, otherwise they're not ions, are they? So I must remember to put the charges on my ions. Okay, so let's stop there, stop the recording there.